measure when you turn 5/2.
Okay.
I'll put it in, but like I don't know how to do it. You still lose. So all we gotta do is like the
You're fine.
I need to find my
Yeah, like you even be into
Dude, yeah.
So are you also EC or are you physics?
Me?
Mm-hmm. What year are you?
I'm a master's student.
Oh, that's cool.
I do more basics anyway.
Are you
I literally
doing
don't-
semiconductors?
Yeah. My project's on topological and split lasers.
Oh, that's really cool.
Oh, yeah, this guy works for Zhao, so he's around.
Growth.
Oh, Zhao
I'm an undergrad, though.
35 plus.
She's good.
She's good. Her research though kind of sounds like
Tedious.
tedious. And
It is.
It can be mind-numbingly boring sometimes.
It is.
Yeah.
I'm fine with that
I
though.
want to get away from that.
It's good growth. Yeah.
I do not want to be doing
Do you work in nanotech or degrees?
I mean, so like in nanotech, I'll do MOCVD and stuff like that. But at the same, yeah,
I don't
MOCVD,
believe it 'cause I've never
MOCVD.
seen him there, and I was in the MOCVD room all summer.
How long did it take for you to get trained on MOCVD?
I mean, I work with a PhD student. I would never sell them.
What?
It takes a year to get trained on MOCVD.
Wait, really?
Yeah.
I shouldn't come back here for a PhD.
I mean,
Orphan wants me to.
I've been in a nanotech. I've been in a nanotech
You
West
do
clean room.
MOCVD?
He wants me to do MOCVD.
Well, I think Aegis is learning his like new PhD student. You know, Aegis.
Yeah.
He's doing MOCVD.
But he wants me to completely do all of the fabrication, characterization, and simulation.
Yeah, sorry.
There's no way that you're gonna do it. It takes a year to get trained.
I just sit there and
But, like, our
I
thing-
monitored it for them.
I
They do.
shadowed
It's
the
really
girl-
loud, so.
I shadowed the girl doing the MOCVD for like a month over the
Yeah,
summer, and I will tell you, our thing's like, oh, they say a year, but it's you can probably do it in 6 months. It's a year.
I would sit there and just monitor it for them. They would go in because it's so loud in there. They would sit in another room, like what's that area near the stairs? Like,
Yeah, just
they
like
they
the
would do their work
system.
in there, and I would sit.
Dude, Lauren is like the girl who does like MOCVD too.
Mm-hmm.
She is like deaf to that noise, and I can't deal it because she'll like talk to me, and I'm like, I can't fucking hear what you're saying. It's so
I like the ambient
She's
noise
like,
of
"Oh, I
it.
forget."
What about etch? How long does it take to train on etch?
Etching.
No, MOCVD is like my
What's the
MBE is
issue?
also like,
It says hi. It said hi. He just erased it.
What the hell, bro? It's like
Oh my fucking.
What the hell?
HITO, and then there might be an R.
Why do you observe
Why
the?
do you think about Hitler here?
It literally said hi with an exclamation point. Why do you immediately go to that? I don't. We're doing physics on the board.
He's thinking a lot about Hitler.
Yeah, I don't.
Oh, the fuck? Damn, bro. What the fuck, Nathan?
But I kind of like the noise. I was sitting there and watching TikTok.
No, I like it. It's like it is. Like, I
Mhm.
like ambient noise.
Mhm.
But like when I'm sitting there trying to talk to somebody and they're
Mhm.
so used to that noise that they
Mhm.
forget it's there and they're just like talking to me like this. I'm like, I can't hear them.
Yeah.
I will show you now how you make a material have a refractive index of 100.
What is this one?
Or just infinitely bounces around. That's why I didn't.
Refraction index is like the optical density of the medium. Right?
Mhm.
How slow light goes.
It's like what's water? Is water
1.6. Very low.
in 100? That's okay. They're gonna be retracting, but go on.
Okay, so the method is called electromagnetically induced transparency.
These would be quick.
So,
Oh my fucking god. Alright.
electromagnetically induced transparency is a way of inducing a very strong light matter interaction
Mm-hmm.
between the electrons and the photons. Light. Right?
Okay.
So light matter interaction. So that's the line.
Bro, can you speak up? Because they're the most distracting human beings ever. It's like a lunch. Can you speak up? Because they're like the most. It's like a lunchroom table. Please. Sorry. I can't hear him.
So,
Okay. Which is lit because it gives me an excuse to go to the bath tower every week. I'm going to get a coffee from ATL.
yeah, me too.
But I'm now more confused about
Okay. So electromagnetically induced transparency is a way of making a really strong light matter interaction between the electrons and the photons in the material.
So like, what's mercury? It's like, what are some like
Listen.
Okay, I'm sorry. Yeah.
Mercury is in physics. So what I'm showing here are the energy levels of an atom. Right?
Mhm.
There are 3 energy levels that you can take on.
Mhm.
You can take on the lowest states, the second state, or the third state.
Mhm.
And so in this material, it's like rubidium exhibits this sort of behavior, where the electron can be in 3 different energy levels. I drew these arrows to show the only ways you can traverse these points.
Okay.
So I cannot go directly from 1 to 2.
Got it.
I did not draw an arrow there. Okay, you can only go from 1 to 3, and then from 2 to 3. So if the electron started here, the only way you could get to 2 is to go from 3, to go to 3, and then go down to 2. Right? Make sense?
Yeah, of course, yeah.
So that means the only two paths are 1 to 3. And then you can go from 2 to 3. Go back and forth.
Yeah.
It's permission. Okay.
Yeah.
So, if you wanted to go to 3, actually the state is a little bit interesting. You would have to go, you would start from 1, you would go to 2, then you would, you would
Wait,
go,
yeah, that doesn't work. No, you're
you
fine.
go to 3, then you would go to 2, and then go back to 3.
Yeah.
That's the only way to go from here to here, for some reason. So you cannot actually directly go from here, it's more like indirectly go from here to here, here to here. That's how you get from there to there. I know, it's a little strange.
Yeah.
But directly from here to here is fine.
Yeah.
Okay. So the full picture then looks like this. So in this case, you have these funny little arrows which show the decay rate, gamma 2, gamma 3. Okay. And then...
Put my phone on sleep mode. Sorry.
And the energy difference between these levels is h bar omega 1, 3, right? 1, 3. Energy difference is 2, 3, omega 2, 3. Wait, 1 second.
Yeah, how was it?
Yeah, okay. And so these gammas denote essentially the decay rate. So imagine the electron was here. How long can it stay here before it, relaxes to the ground state?
Yeah.
This is the most.
So if it was here, like, okay, so it's always going to go down. If it's stuck with that 2, what happens?
Then this is this 2 is a metastable state. So
Okay.
if it relaxes, then it'll have to just like somehow decay from here to here.
How?
Directly.
How would it do that?
But it cannot just like directly jump from up. Does that make sense?
Yeah, that's confusing, but I get it.
So, okay, so then omega 3, 1, right? The difference between here to here, or 1, 3, however you view it, is just omega 3 minus omega 1. Same story, 2 to 3, or 3, 2, doesn't matter. Just to have a negative sign in front. Omega 2, 3, omega 1, 3. So you would use your laser such that this is the probe laser. And this is your...
I'm still confused how it goes to 2 to 1, but I'll just ignore that from now.
Yeah, ignore that for now. It's a little... This is your control. I remember this. Okay. So your probe laser, you have a laser at one frequency and a laser at another frequency injected in the same material, right? So you can imagine like a chip that guides light. It has these 2 frequencies. One laser is at this frequency, omega 1, 3 or omega 3, 1, doesn't matter. And the other one is at omega 2, 3. Okay? So they're pumping back and forth, up and down, right? Here,
Yeah.
Like here and here.
Yeah.
So what this causes is that all the electrons here in the ground state and then the second metastable state will be inverted. The
They're going to
population-
accumulate there.
Yeah, well, be inverted over there, which essentially causes you essentially get now quantum interference to occur between these 2 paths, as I said. Because if you want to go from here to here, you need to go here, here, here. Right? And if you want to go from there to there, you have to go here, here. So you get quantum interference here, which causes that the transition from 1 to 2 is forbidden. Meaning that no longer can stuff decay. So this goes to 0.
Oh, wow.
Okay, so this goes to 0, which means that anything that gets stuck here
It's stuck there.
is stuck there.
Wow.
So this means now that any light that comes in near or at this frequency cannot be absorbed. So 0 absorption.
Yeah.
So all of a sudden, the material used to absorb light at this frequency now doesn't. So you have 0 absorption. And on top of that, the refractive index of the material goes to be extremely high. So that, let me look here really quick. So that if we look at the susceptibility of the material chi, which is related to the refractive index, we'll see that for the real part, it will look like something like this. Okay, but without electromagnetically induced transparency. This is the real part. Real part of chi. Okay? And then for the imaginary part, it'll look like this. Right?
1203, exactly, yeah. 1203.
So I'm plotting here omega. Okay? And here I'm plotting chi. The magnitude of it. So imaginary chi, IM, relates to the absorption of the material. This relates to the refractive index, right?
Okay.
So actually, this is not omega. I'm lying a little. This is omega minus omega resonance over omega resonance. And resonance is like when the material is really strongly interacting.
Yeah.
Omega is the frequency.
It vibrates the most,
Yeah,
correct?
exactly.
What is it? Phonon, whatever. No, that's
just
different.
Like it's interacting the most with light.
Okay.
i.e. when it absorbs the most, or when its refractive index is the highest.
Okay.
The story's a little more complex than that. But
No, you're fine.
beside the point. So you can see here, I've normalized it. So this is the frequency minus the resonance frequency divided by the resonance frequency.
Mm-hmm.
So what is this? This is just when omega is equal to omega res, right?
What, so
Plug
what's
that into here, and this
Mhm.
goes to 0.
Mhm.
Right, so that's what this is. You can see it's most resonant here, right?
Yeah.
Because it's the most amount of absorption, right? So most amount of interaction.
Mm-hmm.
Now, and then as I said, the refractive index is like really small, right?
Mhm.
And to look at the refractive index,
Is that at 0?
yeah.
Okay, got it.
It's 0, yeah. When we look at the slope of d real high
Mm-hmm.
with respect to omega,
Mm-hmm.
okay, this is roughly equal to the refractive index of the
Okay.
material. Right, so when we look at the slope here, I should be taking the magnitude first. Roughly equal to the slope. When we take the magnitude of the slope, I mean magnitude by the way,
Mm-hmm.
that's roughly your refractive index, right? So if the slope is like really steep, right, then it's a really high refractive index, right? Makes sense?
Yeah.
So what I'm saying here is that at this resonance frequency, absorption is really high, which makes sense. That's
Yeah,
what
of course.
resonance is. So all of a sudden, that's without electromagnetically induced transparency. So without
Okay.
having these two
This is
lasers, without having these two lasers on
Yeah.
at these frequencies, all of a sudden when you turn it on, what you get is that this part.
Are these two peaks equal or no?
No, not necessarily.
Okay.
It's just general. That's the real part.
Are these absolute values equal?
Sorry.
Are these two absolute values equal? Like,
Yeah.
okay, got it.
It has to be some sort of symmetry. And this is right. So this is omega minus omega res.
So resonance is peak here when this is the most
Yeah, if you
negative.
plug in omega res, this
Mhm.
goes to 0. So this is 0.
Mm-hmm. Makes sense.
So this curve here,
Oh, you have to like put it on common.
right? The imaginary part is 0.
Mm-hmm.
0 absorption.
Yeah.
Originally you had a lot of
Yeah.
absorption.
It causes.
And now look at the real parts here. Well, it's like this, and then it's a really big slope.
Yeah. I see. Makes sense.
The refractive index increased, right? Because remember,
That's what's scary. It's like I actually
Yeah.
real parts, right?
did it by
Mhm.
0.01.
So the refractive index is extremely high.
But it's not. It's just
So that's effectively what you get end up happening.
Wow.
Material after that happens. I won't go into the math because
It's in a lot of math.
so
Could you send me that?
I mean
Or
you won't understand. So
just it looks cool, honestly.
it's my notes.
You take really pretty notes. I mean, mine's always crazy.
Yeah, but there you go.
That was cool.
Effectively, you can engineer this if you have like a piece of silicon
Mhm.
and you dope it with rubidium atoms.
Mm-hmm.
Rubidium has 3 energy levels.
Yeah,
And,
which
like,
we
silicon
see. Yeah.
has 2 energy levels.
Mm-hmm.
So if you shine both probe and control in that silicon wafer,
You shine what?
If you shine laser lights at both omega
Like
probe,
what nanometer? Like
at omega probe and omega control, whatever that is. for
whatever.
the two,
Okay.
you would figure it out yourself. Then you would get EIT to occur,
Mm-hmm.
and then your absorption that would be
Yeah.
vanishingly 0 pretty much.
Yeah.
And your refractive index would be incredibly large.
Yeah, it makes sense. Wow.
So that's how you would do it.
Yeah, that's interesting. I mean, you explained it well.
Yeah.
Yeah, she fixed that on her second. She fixed it.
So it was easy.
Yeah.
So you find this stuff most interesting then?
Yeah, and this is really interesting. I mean, think about like you can make light matter interactions really strong
Mm-hmm.
in a material which does not exhibit naturally strong nonlinearities by
Yeah.
inducing it using different frequencies of light.
So like, would this be UV? Like, do you remember? No.
It's definitely not UV.
Would it be higher than that?
Just
Lower?
depends on what the
Okay.
As I'm showing here pictorially, typically a probe will be larger than pictorially. Right? This is a larger.
So these are two different nanometers you would use then.
Yeah, I mean,
Or not nanometers. Sorry, it's EM in general. I'm using nanometers. It's always nanometers that they use. Yeah.
So that's what
I shouldn't be using that, but you know what I meant.
Yeah. So that's what you would get for.
I just have no drive to do my
That's really cool. That's
So
really.
silicon roughly has a refractive index of like 3.5.
So like, what's a super high naturally like?
3.5.
That's like that's high.
Super high.
Okay.
But we can boost that up to like 100.
That dude. So what does that have any application to the world?
As I said, light matter interaction.
Okay.
So, like nonlinear optics.
Okay.
Optical solid optics of three-dimensional oscillator.
Mm-hmm. And what's that do? Like, what can that be used in?
Well, there are some classes of problems that can actually be solved using optics, like the Ising-Hamiltonian. The Ising-Hamiltonian is the Hamiltonian that describes the two-state paramagnet.
Okay.
How much energy is stored, and of course things tend to naturally be in the ground state.
Yeah.
So we can solve that problem, which is well known to be NP hard, using optics.
Okay.
So,
And solving that problem, what does that do?
well, it's been shown, I think, in like a paper from 1980s, that if you can solve the Ising-Hamiltonian problem,
Mhm.
then you can pretty much you can solve any NP hard problem.
Okay.
So if we can solve that, then there's just some way we can generalize it using.
Like, so the application could be like using internet, like cables, or what can that application be?
Computation,
Okay.
optimization,
Okay.
protein folding is another, right? Same
Okay.
story there, as I mentioned before.
That's really cool. What made you pick optics over semiconductors? Were you always interested in optics?
They're both, I'm not interested in bulk optics.
Okay.
I'm interested in nanophotonics, nonlinear optics, quantum optics.
Okay.
Yeah.
So when did you learn you were interested in this? When did you learn you were actually interested in this? Were you young? High school?
Yeah.
Bro, what did you look up to get in this in high school?
Things.
Like, did you go on YouTube and just look up physics stuff? Like, what got you into this?
I don't know, I've always been obsessed with computational. So,
And what, are your parents? I think I asked you. Are your parents engineers? Like, no. So they're just like, well, we have a genius son, and like,
no.
no. Okay.
Yeah. So it's, yeah. So
Like, did you would you just read papers as like a child? Would you just read papers?
as a child, I don't want to guess at a high school.
Like, okay, high school.
So yeah, but this has application to nonlinear optics.
Okay.
So nonlinear optics. So dealing with light matter interaction,
Okay.
and you can use that for computation.
Okay. Makes sense. How would you use it for computation?
Yeah. So.
That's the question. Can I take a photo of this first? It's quiet in here now. It's nice. Erase that because this is annoying.
No.
You don't have to.
Okay. So.
It's only 50%. Are you sure?
So, you mentioned an XY plane with a grid on it, and each one of those grids, squares on the grid, is an atom.
Mm-hmm.
And it has one electron that can either be spin up or spin down. And then the Hamiltonian, or the total energy describing the system, is just the sum of their interactions, right? The I and jth row, I column jth row, and then multiplied by some matrix sigma I sigma j, which are very simple matrices themselves. And then you sum over all of them, right? So all these magnets spin up and down, interacting with each other. That is your Hamiltonian. We multiply by negative, as I mentioned before, because it's negative mu dot b. So this Hamiltonian is literally the simplest Hamiltonian of any real physical system.
Okay.
But practically it has no application because magnets are not this simple.
So when was this discovered? Like, when was this?
Well, it's named after. I don't know how you pronounce it. Ising or Ising?
Was this like 1800s, 1900s?
So it's
No,
JL.
20th century.
Yeah.
It's 1900s. Okay.
What the fuck is she?
Yeah.
I mean, she updated
Okay.
at 12 a.m.
Got it.
So
You said that
I don't know how you pronounce it. It's even
It doesn't matter. I got
I
you.
say ice.
Is that German?
I don't know.
It's not
Okay,
about-
whatever. It doesn't matter. Maybe it's targeted. Who cares?
Sometimes because you're, for if you look at really closely, you're
Well,
looking at the
solving this
index.
problem
Mhm.
is so that the solution is that its
You don't care about it.
total energy is the minimum, smallest amount.
Okay.
What's the arrangement of
The index
these
will, but you're not worrying about
spins
the
and
index.
what
You're not worrying
location
about
on
the
J
index.
such that
No, you're not. You're just worrying
the
about
total
the
energy of the system is
Look at
zero.
the-
Yeah.
Right? Naively, or it's easy to solve for small scale, but for large scale,
Like
it's actually
comparing
incredibly
the number
difficult.
with the
Okay.
array index, like 120
And
to like
well,
R4,
one way to
which is
solve
like
it
the
is
index.
using optics,
You're not
or
comparing
nonlinear
the
optics
values
rather.
of the index, it's fine.
We're using
So, like,
called an optical
I think
parametric
it's
oscillator.
JLO,
Uh-huh.
and then
OPO.
use J. Yeah, I think we can
So
always
optical
find-
parametric oscillator is essentially
Yeah,
a
but you have to like make
cavity.
Like,
like some place where light likes to live in.
just look up
Okay.
And it resonates strongly in that cavity, so it builds up an intensity to an incredibly high level.
Yeah.
And we can make use of that.
So
So
It would be like two mirrors. How like it turns green over time. Like when you have yeah.
so
the answer is not
uh, what in this case you can imagine, yeah, sure. If you want to imagine a bulk optic case, imagine that light came in here, and these are two mirrors pointing at each
Yes.
other.
It just turns
And
green over time.
It's
Yeah.
bouncing on top of each other, but
But if it's
that's a
based on
cavity.
her- based on her answer.
But
That's not a cavity?
but that's a cavity.
Okay, got it. Yeah, makes
That's a
sense.
cavity. Right? Light gets trapped in there only for specific frequencies, right?
Mhm.
Some frequencies will just go straight through, some will resonate, right?
Mhm.
I'll go.
The question is, if there's a spherical mirror, how would that look? That's another question. But yeah, it doesn't matter.
Yeah.
It starts at 12.
So that's a cavity. But if I introduce this box, which is a crystal,
Mhm.
a nonlinear crystal, which has a second order susceptibility, or a
Mhm.
third order,
Like 10 people already had it.
and this means that it interacts with light
Mhm.
strongly based on its intensity, so this means that it has an intensity dependent interaction with that
Okay.
light. Then you essentially can cause light matter interactions to occur. So what you were talking about before is actually what I'm going to talk about right now.
Well, they don't
This is
give
what
you,
we call an
like, they don't,
OPO,
like, straight
optical
up,
parametric
I don't know about her.
Okay.
When I asked Luke, he just does
so
me and she just told
in
me
this
what
case,
it
we
was.
have some frequency of light, some pump frequency, omega p, come into this crystal,
Mhm.
to this
Yeah, like,
cavity.
the TAs wouldn't
which
do
is
that.
what we
They,
call
like,
an
have
OPO.
them- They don't even know the answer. Like, they
And
don't even
outside
know
of this,
the-
some of it will be omega p, some of it will go through, right? Because it won't be converted, and some of it will be down converted into
Okay.
a different frequency of light.
They're so loud.
I'll tell you what, like,
Wow, why they? It's so hard to pay
That can
attention.
be down converted into different frequencies, like called the signal.
Yeah.
Or just some different frequency. And if we look at this crystal, we'll have two energy levels.
Mhm.
So it will absorb omega p, h bar omega p of energy
Mhm.
from the ground state to this excited state.
Mhm.
And then it will re-emit two photons of half the frequency
That makes sense.
of 2 h bar omega s, such that it will obviously emit a conservation of photons.
Well, today's that day
Mhm.
of us.
Energy conservation.
So this is like if this is like 200 nanometers, this would be like 400, 400. Yeah, makes sense.
No, not with wavelength, with frequency.
Okay.
This is the inverse.
Single
Yeah.
phase.
Okay, got it.
So the single phase version was like,
Right,
dude, that was
HC
a
or
better
lambda.
exam. Why didn't Paul
So no, it's not half the frequency.
Like she tried to
Okay.
write
Yeah, that makes sense. I can't do that math in my head then. I don't
I can't
know.
either for two.
Yeah, of course.
So that's why we look at frequency.
Yeah.
So, yeah, there you go. So essentially it gets converted, but we can make use of this.
No.
Optical oscillator exhibits some sort of bifurcation. It
Mhm.
either exists in a state
No, what I'm saying is that
where
she
it's
gives
called the
you
zero
a little
state,
bit of
Okay.
or in the pi state. So
Pi state?
Yeah.
Why?
So if we look at the phase space representation,
Mhm.
where I'm plotting the momentum of the position of the photon
Yeah.
versus its momentum, an OPO can only exhibit a bifurcation,
Mhm.
two distinct oscillatory states.
They won't be able to
Either
yeah, but they'll be better at
it'll be in this state called the zero state,
Will be better prepared.
emitting photons with this sort of wave function, or photons with this wave
I don't know
function.
if this is actually just read the
They just call that pi. Okay.
Yeah, use
Whatever.
So we have single phase.
Okay.
like pi, e to I pi, right?
Okay.
If that makes sense.
A three phase. we
So-
E to the I, that's negative 1.
Yeah.
Okay.
One,
they just-
negative one.
Okay, that makes sense.
Modeling analysis.
We can therefore encode a bit sort of way right?
Oh,
And
that's because that's binary, in a way. Yeah.
Yeah.
Wow. Okay.
You can encode the zeros, the ground state,
Mhm.
I literally walked out
as this,
Mhm.
and the excited state is this.
Wow. Okay.
And encode that in the frequency based on that conversion strength.
That makes sense.
But on an optical table,
So we finished like
your OPO would look like that. It would look like a bow tie resonator because it looks like a bow tie. I'll draw it out.
Mhm.
The thing that sucks is like we literally had like the same like it was literally like the practice one which she said it would be, but like she was out to get you, like the way she worded it, the way she formatted it, like sometimes.
So light comes in from here.
Yeah.
This is like a mirror, right? So some of the light gets transmitted through here, right?
Mhm.
Gets reflected off here.
She kind of like
Goes through this
did it
crystal,
dirty with, like she gives
right?
you like Henry's instead of just
And then
the
comes
old
back
like
and repeats the
XML
process.
actually
Okay.
bad. She doesn't like tell you what
So-
the frequency is.
It just keeps going.
So you have to like just.
These kind of questions.
Yeah.
Right, so it's a resonant cavity.
Mhm.
And so this here is your nonlinear crystal, right? Could be made of like lithium niobate,
It makes me more convinced.
what we call thin film lithium niobate. Could be
Mhm.
made of beta barium borate, BBR.
Okay.
Could be made of KTPLFN, whatever that is.
Yeah.
Oh, I'll look.
Right? And so here's your output, right? Input, output, right?
Mhm.
So here we're pumping in omega P. Here we're pumping out some omega P, right?
Mhm.
And then some omega S. Or sorry. Yeah, makes sense?
Yeah.
So if you imagine that this is your OPO, right?
Mhm.
I'm not sure if I want to.
And this is your computational scheme for encoding one spin state,
Yeah.
right? So if you imagine you make a bunch of these connected to each other,
Mhm.
and you control each one, naturally, based on the interaction between the light interactions between this crystal and the pump frequency and its intensity,
Yeah.
it will naturally relax to this state, which minimizes this Hamiltonian. I'm not going to go into this super
Yeah, no, you're fine.
It's honestly a little bit beyond me. But,
So this could be better than like a normal, like using electrons.
They tested it with D-Wave, quantum computer. So D-Wave quantum computer.
Nothing. This is for fun.
Conversation.
Yeah.
So, the D-Wave quantum computer can't even solve it. It solves it at n squared, I think.
Mhm.
N squared. It solves it linearly. Has no dependence for short range.
I see.
So there you go.
Dude, that's really cool. So is this the future? Like, do you think this has a lot of application to the future?
Yeah, I think this is the future of computation.
Okay.
But
so
the problem is-
bye-bye semiconductors. Hello,
No,
this.
this is semiconductors.
Okay, this is.
Like imagine if you could integrate this on chip,
I see.
and you can.
You can? You can't.
You can.
Oh wow.
Yeah. So semiconductors are not bye-bye.
Okay, cool. And I guess you can still use growth to grow materials.
Yeah. So you would actually grow. You would have silicon and you would have lithium niobate grown on top,
Mm-hmm.
but a thin layer. That's why we call it thin film. Lithium
So do you guys grow this yourself? No. Who does?
You would buy it because
Not
growing
in-house.
nobody grows lithium niobate on silicon graded.
Okay.
To make high quality.
Yeah.
Because typically the second order susceptibility of the material is anyways really small, and then third order is even smaller, and
Okay.
then fourth order is even smaller. Right?
Wow.
So typically for your future reference.
So do any universities grow that, or is it only like a company? No.
It's always grown. You always buy it from lab. So your electric field strength, the n+1, right, will always be greater than n. So this is what it's roughly scaling.
And you can etch this easy on like a chip or something like that, like fabrication.
I don't know about etching.
Yeah, it doesn't matter. Yeah. Okay. But it's possible, obviously.
Yeah.
Yeah. Okay.
So you make a waveguide, it goes in a big spiral, and that's your parametric oscillator.
And I'm going to assume this has to be way more expensive than traditional semiconductors, right?
Network's still down.
I don't know.
You don't
Oh,
know.
it's you. I thought I'm not
It's just etching, making waveguides.
Oh, I don't care.
So like how long will they're so loud. How long will this take? So it's gonna be like integrating to an iPhone or something like that.
I don't. I just said,
Yeah, you can't.
I just said this Hamiltonian has
Yes.
no real application.
Okay.
I said that before.
Yeah. Dude, this is really cool. I like your research. It's kind of, this is interesting.
attended that lab, so you don't even, doesn't matter.
They're just looking at
No,
this.
because on Wednesday,
Bruh, I'm gonna take a photo of this as well.